My name is Andrew. Can you hear me okay in the back? Is that a little bit better? I can try to angle my face down. The mic's just a little. I'll hold it like this. How's that? All right. Anyway, I'm Andrew. I like running. I like it a lot. Also, hiking is a lot of fun. I am a triplet. My brother here is in the front row. My sister's a giant hippie, but we love her very much. Hang on, let me see if I can go back. That photo was taken at her wedding. It was a whole thing where we all sat in a circle, and we all said something that we love about the bride and the groom, and that was most of the wedding ceremony. I took a selfie with Amy Poehler once. Kinda. I think she may have seen me. I'm not too sure. Anyway, I guess I can get into the talk now. So we're going to go over a few things. Who here has worked with graphs before? A lot of you. Good. So I got to apologize to you in advance because we're going to go over some basic vocabulary first. If you stick with it, we'll get into the interesting stuff. So we'll go over some basic terminology, things like node, tree, forest, graph. I'll sort of motivate the talk with a common problem that you see when you're dealing with graphs. A lot of the time, you'll have the operation where you need to go and fetch a lot of nodes from the graph in order to do some kind of computation. So we'll take a look at some code there, and I'll present our solution for doing computations on sets of nodes. Followed by a practical example of exactly how we implement that. Some architecture for how it's implemented, because the example is going to be mostly code that assumes an architecture exists sort of behind the scenes. So we'll take an in-depth look at that, as well as some edge cases that you encounter with our particular solution. A structure for handling those. And then we'll go over a couple of interesting algorithms. Does anybody know what a reproduction number is? A reproduction number is, it's in a social graph, for example, it's the number of shares per share. And then the other algorithm that we'll take a look at is cross-network propagations. Something that we do at BuzzFeed is we're interested in how posts travel from one user to the next. And one of the things we do that's unique from other organizations that are doing something similar is we're actually able to track that across different networks. So we can see shares on Facebook, on Twitter, on Pinterest. It doesn't really matter. So we can get started with some basic vocab. It all starts with a node. And a node is interesting. It has some attributes. It can represent a user in a social graph, or it can represent, say, a bill that's going through Congress, a congressman, a disease. You can look at groups of nodes or objects, and if you want to call them that, entities, and analyze them as they are. But when you add an edge, can you guys see? Yeah, I guess you can see that. It gets pretty interesting. So when you have two nodes, you can draw an edge between them in a lot of cases, and that edge represents some kind of relationship. If the two nodes are users on a social network, that edge can represent a share. So maybe the first node has shared some piece of content with the second node. If it's a node in if maybe the node represents a bill, the edge could represent two senators co-sponsoring that bill together. If it's a disease, then maybe two people are infected at the same time. If we draw some more edges coming out and add some more nodes, we get a tree. And I know what you're all thinking. Peace. So a tree has some specific properties. I don't know if you can see these, but the edges have a little arrow at the tip that indicates they're directed. So a tree is a directed graph that doesn't have any cycles. So you can start at one node, and traversing only in the direction of the edges, you can cover all of the nodes in the graph, assuming you're starting at the root. In our case, the tree has one parent per node, and each node can have many children. So for example, in this case, this is the root node of the tree. This is the child of that node, and this is the grandchild of that node. You can start from the bottom and say this is the parent of that node, and that's the grandparent. You might also hear the terms ancestor or descendant. They're all basically the same thing. Different words for the same thing. Things, sorry. So if you draw an edge in the other direction, then we have a graph, and we've introduced a cycle to the tree. So it's more of a general data structure. A graph can be a superset of a tree, and something that you might see that's relatively common is a spanning tree for a graph. If you find the spanning tree, it simplifies a lot of operations that you might do on a graph. So multiple trees form a forest. It's a set of disjoint trees that and it might help at this point to bring up a concrete example. If our users in a social network, or for example, users of BuzzFeed.com are represented by nodes, and the edge is a share event between two users, then a user might originate by arriving on a page on BuzzFeed.com, sharing that with their friends, and their friends share it with each other. A distinct user can arrive on the same page and share that with their friends. So that's how you get two separate trees in a real-world example. So now let's talk about a common operation to sort of motivate the rest of the discussion. So this is a function that we can use to start at any node in a tree. Sorry, I guess I should ask, are there any questions about the basic vocabulary at this point? Cool. So we can start at any node in a tree, and this function will yield all of the downstream nodes from that node. We use yield so that we only use as much memory as we need. We use a queue, and we don't have to keep a list anywhere besides the queue itself, which is pretty memory efficient. This is a decent approach to iterating over a tree to return all the downstream nodes. As far as lookups on the nodes, can anybody tell me what the time complexity of this would be? Anybody? It would be, it's actually linear in the number of nodes. So in the number of downstream nodes, it's linear in that set. So if V is all of the downstream nodes, then the cardinality of that is the time complexity for this particular algorithm. So that's not fast. It's not slow. It's good. If you have a very large graph, though, sorry. If you have a very large graph, like say V is 1 million, 2 million, 3 million, it can start to add up. So a small amount of savings can really get you a lot of benefit. If you use, so does anybody know the best this can get? The best you could possibly do? You have to return every node. You don't have to visit every node necessarily. Well, in the case you already have all the nodes stored somewhere, you can just look it up in, say, a hash table, in which case it would be order 1. But in practical situations, you might use a primary key lookup in a binary tree, which is order log V, which is that's the time complexity of a binary tree lookup, like the default index in MySQL, which I'm sure a lot of people are familiar with. So the other approach in MySQL is to use a hash index, in which case it's order X, which is the bin size for the hash. So there are some number of collisions if you're using a hash in practical scenarios, and it's slower than order 1, but it's faster than the other two. So to state the problem that we address on our team, something that's to make this just very practical, is accessing nodes quickly enough to compute the number of statistics at runtime while avoiding a monolithic design. So we need to look up nodes quickly in order to compute statistics on them. And if we're looking up, if we don't have those ready, and we're computing a number of statistics, we run into some problems. The runtimes can be very slow if you get to the millions of nodes, and then the computation on top of that keeps the user waiting. So our team has recently been tasked with building a dashboard that computes a lot of statistics on graph data. We can compute the reproduction number, the maximum depth of a tree, the number of nodes in the tree. All of these things require traversing the tree, and if you're trying to add more statistics or remove them, then you add them to the same process, you end up with a monolithic design, which is difficult to maintain. Has anybody in the room worked on a project that was sort of research track? Something that maybe they were looking to publish at or hadn't had the problem fully explored before they started the project? Anyone? So if you're in a situation like that, you might find that your requirements change. So sometimes, so we can have a product meeting and somebody will say, we'd like to see the reproduction number, the depth, the breadth, the viral index for a tree. And if you want to compute all those, if you want to make that easy to program, then you're best off keeping the algorithms very separate from the actual code that fetches your nodes and any sort of traversal query sort of complexifies them. So we come up with a solution. We build all of our trees in real time. As we receive edge data from the website, from BuzzFeed.com, we incorporate it into our graph as they come in, so just as quickly as possible. So let me explain a little bit how that works. We start with a user. So this is a user on our site. And when they arrive at a page, the user sends an edge, assuming they came in from a share event. So it starts out, somebody clicks a link on Facebook or on Twitter or on Pinterest, and then they arrive on the site, and we receive an edge, which is just it's a data model that contains the person they receive the information from, a unique identifier that's randomized and anonymized, as well as their own unique identifier. So that event is what we use to represent a share. It has a timestamp on it for the time that it was created. This allows us to tell what order the shares came in and through, and we can reconstruct the tree in that way. So when we get the edge data, it goes into an API, which we're actually running NSQ. It's a message bus that's similar to Kafka or RabbitMQ. Nice. So you know NSQ very well. Yeah, I work with Matt now, and yeah, that's the guy. So small world. So anyway, Matt. An edge gets coming to the Stream API for whatever reason, network outages, maybe a client went down or a worker machine, then we can count on it being redelivered, and we can tell where it goes based on what time it came in and the parents and children. I'll go into a little bit more detail with that later. So our edge data goes from the grow trees process into a database. And out of the database, we get some context about the sort of location in our tree, in our forest, that edge was located. So it tells us things like the out degree, the depth, the node name, the parent name, the child name, if we want it. The context data structure is pretty versatile, and depending on what algorithm you're implementing downstream, you would want to include or remove certain attributes. So that's sort of catered to the particular use case, but kind of more is better. If you want to be able to add and remove statistics that you're calculating online, then that context data is something that you would have to change. So it's better to have more attributes and not have to change it that often. So out of our grow trees process, that context that comes from the database, and we stuff it into a structure that's nicely readable. And we call that a growth statistic. So that tells us in what way our tree has grown having added that edge. So we shove it back into the Stream API. And then the growth statistics are what go to our online algorithms. So who's familiar with an online algorithm? Does anybody care to explain exactly what that is?